how do I take an empirical formula and turn that into a molecular formula? After I've done all that homework, take my percents, turn them into grams, grams into moles, moles into mole ratios. How do I turn that into what the real molecule is? What do I need to know? Well, on the bell work today, we had NO2 and N2O4. What could I measure about those two that would show me why they're different from each other? Well, how would they be different? Their molar mass, right? So its molar mass is the difference. Since the empirical formula is the lowest ratio, the real molecule has to weigh at least that, because it's the lowest ratio, or it's going to weigh more. If it's the lowest ratio, that's the least it could weigh. So if I figure out what the lowest ratio weighs, figure out what the empirical formula weighs, I should be able to tell the difference between NO2 and N2O4. But when it weighs more, could it weigh 2.7 times more? No, because I got to have whole numbers the whole way, right? There's all integers, right? So when it weighs more, it's going to weigh a whole number times more, not a whole number ratio, a whole number. It's going to be twice as heavy, or 3 times as heavy, or 4 times as heavy, or 72 times as heavy. Well, probably not 72. But it's going to be a whole number times heavier. N2O4 was twice as heavy as NO2. One weighed 46 grams per mole, the other weighed 92. Twice as heavy. So I need to figure out how many times more. So what I need to do is take the actual molar mass and divide it by the mass of 1 mole of the empirical formula. Figure out how heavy 1 mole of the empirical formula would weigh. So take the real one and divide it by what the lowest ratio weighs. That will tell you how many lowest ratios you have. When you do that division, you'll get a whole number. If you get a 1, that means the empirical formula weighs the same as the molecular formula. The two are the same. If you get a 2, the real molecule is twice as heavy. So you would multiply all the subscripts by 2. So you multiply the empirical formula by how many you had. Division tells you how many of those empirical formulas you had. You either had 1 or 2 or 3 or 4 of them. It's pretty basic. Let's see what it looks like. The compound has the empirical formula of ClCH2. A molar mass of 98.96 grams per mole. What is its molecular formula? So, the ratio, I got Cl, 2 C's, no, C and 2 H's, sorry, C and 2 H's. So 1 mole of Cl is 35.45 grams. 1 mole of C is 12.01 grams. 2 moles of H is 2.02 grams. Cl is the only one that doesn't look real familiar there, but I got all those off the periodic table. You add that up, that's 0.48, and 35 and 12 is 47, and 2 more is 49, 49.48 grams. So the empirical formula weighs 49.48. The real molecule weighs 98.96 grams. You get 2. So the formula is not ClCH2, it's, well, got twice as much of everything. So it's Cl2C2H4. Because that would have the lowest ratio of ClCH2, and it would weigh 98.96 grams. It would be both right criteria. It's got the right empirical formula, and it weighs the right amount. So all I did was take the molar mass they gave me and divide it by what the empirical formula weighs. Pretty straightforward. But don't forget, where the heck did I get ClCH2? Somebody told me a percent. I took those percents, changed them into grams. Take the grams, change them into moles. Found the mole ratio. There's twice as many moles of H as there was C and Cl. All the things you did yesterday to get to this point. Right? All those things we did on the homework last night and the day before get you to this point. And then you do a division problem. Oh, these are getting long, aren't they? Okay. Hey, there's a carbohydrate out there with a molar mass of 180 grams. What's its molecular formula? That's its empirical formula. That makes it a carbohydrate. What is its molecular formula? Well, one mole of carbon would weigh 12.01 grams. 2 moles of hydrogen weigh 2.02 grams. 1 mole of oxygen would weigh 16.00 grams. So that's 3, 0, 10, carry the 1. 30.03 grams is how much 1 mole of CH2O would weigh. The real molecule weighs 180 grams, divided by that 30.03 grams, it's a 6. Because 3 times 6 is 18. 6. So, what's my formula? C6, not 2 H's, but 12 H's, not 1 O, but 6 O's. It's glucose. That's right. So we always have some uncertainty of those last numbers. And it's going to come out really close to a whole number. You're not going to get perfect data. Always round a few times along the way. But think about where I got CH2O from. It's a pain, isn't it? Think about what it's going to take to do all of that for homework tonight. It'll work if you want to do it. And actually, on some of the homework, you have to do it that way. But there is a shorter way. If they give you percentage and the molar mass, and they want the molecular formula, so they give you percentages that we use to turn into empirical formulas, and the molar mass that we talked about today. I could do it, take the percents, change them into grams, grams into moles, moles into mole ratios, find the empirical formula. Then find out how heavy the empirical formula is, and divide it, and it would tell me how many of those empirical formulas I had. That would solve this problem. I know how to do it that way. But there's an easier way. Okay? When we do percentages, we take the percents and change them into grams by assuming 100 grams. I'm going to pick a different amount. I'm going to pick the molar mass. I'm going to multiply the percentage times the molar mass. So just like on number 5 with A and B, you can figure out how many grams of each chemical there were. I can figure out how many grams of each element there are in a mole of the compound. I'll get grams of an element, and that will be that many grams in a mole of the compound. Make sense? If I take, if I got something that weighs, it's got a molar mass of 100, and it's 12% carbon, I got 12 grams of carbon. If this molar mass is 50, right, and it's 12% carbon, 50 times 12% is 6. I got 6 grams of carbon. Take those grams and change them into moles. When you do that, what you're figuring out is how many moles of that element in a mole of the compound. And that has to be a whole number. In a mole of water, you can't have, in a mole of a compound, you can't have half a mole of an atom. You've got to have at least one whole mole of it. Now, notice this doesn't say whole number ratio again, it says whole number. A 1, a 2, a 3. That's your subscript. If you've got a compound that has 3 moles of carbon in it, that's C3. If you've got a mole of a compound and it's got 3 moles of carbon, that's 3C. Okay, that's it. Those are your subscripts. We're done. It's shorter because we picked a different amount to start with. If we pick 100 grams, then we got to turn the percents into grams, then we change the grams into moles. Right? But extra step. So let's try one. Caffeine. I gave you these numbers for caffeine last week. Liquid sleep. Remember, we figured out the empirical formula for liquid sleep was what? C4, H5, N2O, or I think that's what it was. I can't remember. We'll find out because we can do this. So caffeine. So I've given you the same numbers for caffeine. All I did was add the sentence. You're right. It's got a molar mass of 194 grams. What is this molecular formula? Now, if I got this, I can do what I just did. I want to show you that the percent way works. So I need 49.48% carbon times 194 grams. The percent times the what 1 mole weighs, 49.48 times 194 divided by 100, and I get 96.0. There's only 3 sig figs. Grams of carbon. Take those grams of carbon, change it into moles of carbon. 1 mole is 12.01 grams. I divide that by 12.01, and I get 7.99, which is 8. So in 1 mole of my compound, I can now say I have 8 carbons. So it's going to start off with C8. Okay. Same thing with hydrogen. Take 5.15% hydrogen times the 194 grams divided by 100, and I get 9.99 grams of hydrogen. Change that to moles. When I divide 9.99 by 1.01, what number am I going to get? Something really close to 10, right? I think you get 9.96 or something like that. So, that's 10. H10. %16.49% O times 194 grams. And I get 32.0 grams of O. Grams of O to moles of O, 1 mole is 16.00 grams. I don't need a calculator. That's 2O. 2 for O, right? Not 22O. 2. Oh, and I forgot the N, didn't I? Yeah, let's put the N in there. 28.87% times 194 grams is 56.0 grams of nitrogen. Grams of nitrogen I have to turn into moles of nitrogen. One mole of nitrogen is 14.01 grams. And 56 divided by 14 is 4. Technically, we should write the N in there, but I'm not going to get you about order on those. This saves us a step. It saved us 2 steps along the way because I didn't have to do that division and find the lowest ratio. And I never added up the empirical formula. Right? So I get to save those 2 steps. I don't have to find a mole ratio, and I don't have to figure out an empirical formula mass. But can you see that it does have that empirical formula? Just twice as heavy as the lowest ratio. Really difficult? I mean, doing these problems gives me a headache. When I get a headache, I need some ibuprofen. Tylenol. Okay, ibuprofen is 75.69% carbon, 8.80% hydrogen, and 15.51% oxygen. Has a molar mass of about 207. What is its molecular formula? So which way you want to do it? Take the percents, turn them into grams, grams to moles, moles to mole ratio, get the empirical formula, add that up, and divide 194 by that number. Or the shorter way. Take 75. It doesn't let me write in that little spot on my screen. (75.69% carbon times 207 grams, 75.69 times 207 is 156 grams, 157, sorry, 157 grams of carbon. Grams of carbon to moles of carbon. 1 mole is 12.01 grams. Do that division, I get, with 3 sig figs, 13.0. So that is C3, or C13. Now the hydrogen, 15.15%. Oh, no, 8.80%, sorry. 8.80% hydrogen times my 207. And, oops, I did 8.08, not 8.80. I get 18.2 grams of hydrogen. Take the grams of hydrogen, turn into moles of hydrogen. 1 mole is 1.01, but I'm guessing that 18 divided by 1 is going to be really close to 18. So that's H18. And then, finally, my oxygen, 15.51% oxygen times the 207 grams. we get 32.1 grams of oxygen, and it's 16.00 grams for 1 mole. 32.1 divided by 16 is going to be really close to 2. So that's my formula. Well, real molecular formula is C13 H18O2. So, what's its empirical formula? It's the same thing. So that's what the real molecule is, and it's the same as the empirical formula. Remember, they can be the same. So if you had done it percents to grams, grams to moles, and done the mole ratios, you would have gotten 6.5 to 1 for oxygen and 9 to 1 for hydrogen. 6.5 is 13 halves. 9 to 1 is 18 to 2. Make sense? So, and this is what your homework looks like. I do want to point out something about it. It looks like we haven't talked about that in forever because we haven't really needed to, because we never talk about it that way. People just, okay, the AMU.